Very pleased to have Cornelis join us now from TU Delft in Netherlands. This is somebody who's well known to some of us, and in particular to Evert, which I was very grateful for. Evert's done had some conversations with Cornelis, and I had to talk to him. I was fascinated having a chat with him about how you can realize these chart datums and connect them with mainland height systems. It's following the workshop that we did in Indonesia. This is a particular gap that I definitely have in my knowledge base. And as Evert mentioned this morning, what we're trying to do is connect with people like Cornelis who've done some of this work and can guide us as to bring those maritime data sets into the same frame of reference that we have for the hiding onshore, and using that geoid model as the connection between them. So Cornelis has done some great work on this in his region, and today he's going to share with us his experiences and give you some thoughts and suggestions on how you can progress this within your countries. So thank you so much for joining us. I really appreciate you joining online early this morning. It's great to have you here. So with that, I'll pass over to you, and we greatly look forward to your presentation. Thank you very much.
Thanks. Well, good afternoon, everyone. I hope you are having a productive and inspiring workshop so far. It's a real pleasure to join you virtually from the Netherlands, and I want to thank the organizers for the opportunity to contribute to this really important meeting. So as Nick just said, my name is Cornelis Slobbe, and I'm an associate professor at Delft University of Technology. The topic of my presentation today is closely tied to my PhD research, which I completed in 2013. Since then, I've worked with a team from TU Delft, governmental agencies, knowledge institutes, industry partners, to turn that research into practice. And this job was finished for the Netherlands in 2018. As Nick said, today, I hope to share some of our experiences with you. And my focus will be practical. So by the end of the session, I hope you will have a clear idea of what it takes to implement a chart data model, where to begin with, what to watch out for, and what the possibilities and impossibilities are of various strategies. And right at the outset of my presentation, I would like to emphasize that this is an interdisciplinary exercise. It's not just about linking reference surfaces. It's about bringing together different professional worlds, disciplines, where each of them is holding a part of the solution. To begin with, I will discuss why we need a model for chart datum. I will then define what chart datum is, with a particular focus on lowest astronomical tide. Following that, I will present the first strategy for deriving a chart data model, along with several variants. In this presentation, I refer to this group of methods as the ocean tide model derived chart data model. And forgive me, this is my naming, which I just use in this presentation to distinguish it from the second strategy that I refer to as the Dutch approach. And I call it the Dutch approach because it was developed during my PhD research and now implemented in the Netherlands. Finally, I will explore the role of satellite altimetry in modeling tides and by extension chart datum. And I will explain why existing altimeter-derived tides models show limited accuracy in shelf and coastal waters, and outline a way forward. And this approach forms a cornerstone of our strategy that we want to pursue to develop a global chart datum model. First, I would like to outline why we need a model of chart datum. There are basically two needs. The first one is because we would like to integrate land and sea data sets, which we can do if in both domains a different vertical reference is used. At sea, this is chart datum, which is defined by a particular phase of the tide. Heights on land refer to a vertical datum that historically was realized by means of spirit leveling, that may or may not have been combined with gravimetry. And I guess this is the topic of the next talk today. I'm not going into details here. The datum point may have been defined by a particular water level or mean water level at one or multiple points. And the reference surface is approximately a level surface. And the heights are consequently called physical heights. The vertical datum was not accessible at sea. In fact, the spatially varying relation between both the mainland height system and chart datum is only known at tide gauges, provided these are connected to the mainland height system. If our aim is to integrate land and sea datasets, we need to establish the relation everywhere. And this is achieved once we know both the land datum and the datum used at sea in 3D space. But here's the second reason. For the vertical datum used on land, we often have a description, such a description available. And that is developed because we want to exploit GNSS in determining physical heights. This vertical reference system is the geoid or quasi-geoid to which a corrector surface may or may not have been added to connect it to the zero height surface as realized from leveling. Although the quasi-geoid or geoid is defined both on land and sea, the vertical reference surfaces were typically computed for the mainland region only. At least this was the case in the Netherlands. At sea, obviously, we also want to make use of GNSS in determining depths. For this, we also need to know the ellipsoidal heights of chart datum. So, to enable what is known as ellipsoidally referenced surveying, we also need a model of chart datum with respect to the ellipsoid. Of course, this model must cover the entire domain where chart datum is used as the vertical reference for depths. For the Netherlands, this covers the entire exclusive economic zone that is on the map shown on the right-hand side of the screen, the area that is not white. The coastal waters, very important. The Dutch Wadden Sea, so any inland sea, the estuaries, and even part of the rivers. The question that I would like to address today is how to obtain such a model. By the way, in my presentation, I will skip the problem of how to realize a chart data model in rivers. This was not part of our project anyway. And I think the accuracy or the approach that you use in rivers is more or less, is in fact well known. So I focus on all other waters that I just outlined. Let's go back to the definition of a tidal datum. As I just said, a tidal datum is a reference surface that is defined by a certain phase of the tide. That can be anywhere. However, the International Hydrographic Organization adopted one particular tidal phase as chart datum. And that was in order to support safe navigation. This reference surface was the lowest astronomical tide level. I should make clear that this adoption only involves oceanic tidal areas. In mixed, inland, or non-tidal waters, the IHO recommend other chart datums to be used. Lowest astronomical tide is the lowest tide level which can be predicted to occur under average meteorological conditions and under any combination of astronomical conditions. Besides this definition, the IHO resolution also includes the following recommendation. It is recommended that lowest astronomical tide and highest astronomical tide, which is by the way used for indicating clearances below bridges, for example, has to be calculated either over a minimum period of 19 years using harmonic constants derived from a minimum of 1 year of observations, or by other proven methods known to give reliable results, and the resolution states that it needs to be accompanied with an uncertainty measure. So what we need are observed water level records. And essentially, I would say there are 3, maybe 4 techniques that are typically used to provide those records. There are, of course, tide gauges, well known. There is GNSS buoys or GNSS reflectometry. And we have satellite radar altimetry. These are different techniques with different properties, different characteristics. I'm not going to discuss all of them. I put them on the slides just as a reference. The main aspect I would like to emphasize is that tide gauges offer high temporal resolution and some coverage in coastal regions, while satellite radar altimetry provides broad spatial coverage over the open ocean, which means that in realizing the chart data model, both are essential and both are needed. Let's now come to the first strategy that you could exploit in order to compute a chart data model, which, and again, this is my naming that I use in this presentation, I refer to as the ocean tide model-derived chart data model. The approach that is probably most close to our hearts as geodesists is a solution in which we rely on observation only. The strategy that we could employ in order to realize such a model is to combine chart datum estimates from altimetry-derived tidal atlases. These are known as empirical ocean tide models, and the mean sea surface model with estimates derived from tide gauge records. There are several of such models available. You have the model produced by DTU Space, which is regularly updated. The latest version that is publicly available is DTU 23. It's the EOT 20 model. It's a model produced by DGFI T2, a German model. And you have a model produced by Richard Rey. It's the GOT 5.6 model. I'm not going to discuss the differences between those models, but there are differences. There are differences in the estimation procedure that is used to estimate the tides. There are differences in the data being used. Different altimeter missions are considered. The time span differs. Whether how to deal with data outside of the topics JSON, let's say area, so that is above 66 degrees latitude. There are different strategies in use. The spatial resolution of the model differs. The constituents being estimated or inferred are different. And there are differences in the way the self-attraction and loading tides or contribution are considered. For example, in the EOT model and the GOT model, the loading tides are separated from the ocean tides. What is a statement for you as a user that I would like, a message that I would like to convey is that no single model performs best in all regions. As an alternative, and then you do not only rely on observations anymore, you may use or consider the usage of assimilative ocean tide models. And these models combine numerical modeling with data assimilation. And data being considered includes satellite radar altimetry as well as tide gauges. I would say that there are two models available that you could use for this purpose. There is the well-known FES model that is produced by the French people, CNES in particular. The latest release is FES 2022b, and you have the TPXO model that is produced by OSU. If you compare these models to empirical ocean tide models, there are few differences that are striking. First of all, that in these models, tide gauge-derived tides are already incorporated, although it's a limited subset of the total amount of observations available. They are produced at a slightly higher spatial resolution, 1/30 degrees, and they include basically more tidal constituents, although many of them are not improved by data assimilation. Having said this, the accuracy of these models is not necessarily better than what you obtain from the empirical ocean tide models. And just as an illustration, I include this result that was a validation conducted by some Chinese colleagues in the Eastern Chinese Marginal Sea. They basically considered most recent models that I just introduced. And as you can see, that in this area, if we consider the 8 major tidal constituents, it is the EO2 model that has the best performance. Again, in any other area, this may be different. So let's now come to the procedure. We have a tidal atlas that is basically estimated from satellite radar altimetry. What we need to do is to compute from this atlas the separation between chart datum and the mean sea level. And here's the grid guide. So essentially, you select the tidal constituents of interest. Of course, you may use all, but there is an option to combine constituents from multiple models. For each grid point, you are using or applying an harmonic synthesis in order to determine the minimum, to determine the tidal water level over a time series of at least 19 years. From this time series, you determine the minimum tidal water level. And this is, if you, of course, stick to LAT as the chart datum, and you interpolate this to the desired output grid, and you have a grid, a model of chart datum with respect to the ellipsoid. Of course, you may want to combine this with chart datum estimates produced by or obtained from tide gauge instruments. And here you can also use harmonic analysis in order to estimate these values. What is, however, of utmost importance, and that is maybe the most difficult aspect of this entire exercise, is to remain consistency. So this is the buzzword, consistency. And that needs to be maximized to guarantee agreement between the LAT derived from satellite radar altimetry / ocean tide models and the tide gauge record. And consistency needs to be maintained in terms of the analysis period, the reference epoch, the treatment of radiational tides, treatment of the permanent tide, the impact of vertical land motion, the geodetic datums being used, and so on. I'm not going to discuss all of them. Most, I think, speak for itself. What I would emphasize is the third one, so the treatment of radiational tides. The issue is that if we look at the water level variability, there are, let's say, processes like mean sea level pressure variations that also have energy at tidal frequencies. So when you do the altimeter data processing, You want to remove as much as non-tidal signal as possible. So it includes a correction for these wind-driven, mean sea level pressure-driven variations. As such, part of, let's say, the energy at the tidal frequencies is removed. Well, this is typically not done when you do the harmonic analysis on a tide gauge record. And there is one source of an inconsistency. There's another issue that concerns the use of tide gauges in river mouths. Here you see a photo of the new waterway that is the main entrance to the port of Rotterdam, but also a location where large volumes of fresh water are discharged in the North Sea. And here is the location where we do tide gauge, where we have our tide gauge. One of our PhDs investigated the water level variability that is associated with changes in water density. And as expected, this variability is influenced by the tides. At high tide, salty seawaters enters the new waterway, while at low tide, fresh water is discharged into the North Sea. So the steric water level varies with the tide. By comparing the M2 tidal amplitude estimated without and with accounting for this effect in the model, we found a reduction of 7 centimeters, which is about 9% of the tidal amplitude, the M2 tidal amplitude. At the nearby tide gauge, however, this effect was gone. Okay, then you have your model of chart datum with respect to the mean sea level, and you have a set of point estimates at the tide gauge locations. How to combine them? Well, I think this procedure is well described in literature. The Canadians and also in the UK exploited weighted interpolation to do so. If you opt for a weighted interpolation strategy, I would recommend the approach that is described by Turner et al. And why this approach considers the use of what is referred to as sea distances. So the distance between 2 points, the computation point and your observation point, is not the Euclidean distance, so the shortest distance over the globe, but it's the shortest distance over sea, which makes sense in case you have a complex coastal topography or islands. Then we need a mean sea surface model. And these mean sea surface models are typically computed by satellite radar altimetry. A bunch of them are publicly available, but there is a caveat here. So in order to use them in computing the ellipsoidal heights of chart datum, you need to restore the time averaged contributions of any correction that is applied in the processing of the satellite altimeter data prior to computing the mean sea surface. Notably, you need to restore the time averaged dynamic atmospheric correction. Then some people, including the colleagues in the UK, even used tide gauges equipped with GNSS in order to increase the accuracy of the mean sea surface models in coastal waters. Having both a chart data model with respect to the mean sea level and the ellipsoidal heights of the mean sea surface, you can add the two together and you have your chart datum model. Luckily, this is not something that you need to do on your own. There are multiple models available that are computed this way and that you can download. I know for sure that DTU has computed an LAT model, which is publicly available, and CNES It might be, though, that they are both computed with an older version of the ocean tide model than what is now available. So that is something to consider, but for sure, they will update it in probably near future. Now you may wonder, the tidal models that we considered so far have all been global models. Probably you may have access to a regional tide search model that in your country is used for storm surge prediction. The question could be, how can we exploit this model for chart datum determination? Well, these so-called tide search models are two-dimensional numerical models that solve the shallow water equations. Unlike the global ocean tide models that we considered so far, which provide grids of amplitudes and phases for a predefined set of tidal constituents, the tide search models output time series of water levels. To compute a chart data model using this approach, the model is run with tidal forcing only. The resulting tidal water level time series can then be used in the same way as before. This is the method that is employed in the UK WRF project. It is also worth to know that such regional models are typically calibrated using tide gauge observations. Here's the flowchart, and I've used the dashed line to indicate that the tide gauges have been used to calibrate the model, probably or likely. And this is done, for example, by adjusting model parameters such as the bathymetry. The quick guide is, you take your model, you force it with tides only. For each grid point, you determine again the minimum tidal water level over a 90-year period. You interpolate the resulting the gridded values to your desired output grid, and you have your first component of your chart data model. And otherwise, the procedure continues as I just outlined before. Now the valid question is, what can you say about accuracy? And I should be honest that we did not test these variants ourselves. That's the first thing. The second thing is that determining of accuracy is a non-trivial issue due to the lack of independent estimates. But we can learn from what others did. And I in particular had a look at what is produced in the context of the already mentioned UK WRF project. It's published in 2013, a paper by Eliva and colleagues, where essentially they conducted a whole bunch of error analysis. And the key message was that their surfaces meet the target accuracy of 10 centimeter onshore and 15 centimeter offshore. And this is the standard deviation. As part of the assessment, they conducted fieldwork where they completely independently from any data that has been used before, estimated or computed the ellipsoidal heights of chart datum at 6 locations surrounding the UK. And as you can see, the differences between chart datum at these locations derived from the observations and their model reaches up to 70 centimeters. This is quite a lot. Another component of the accuracy assessment can be found in the paper that I already cited, the one by Turner et al. There, this publication includes 2 tables where they compared the tide gauge derived chart datum estimates with respect to the mid-sea level to the model derived ones. And that was done prior to the combination of both data sets. If we zoom in to the top 2 models, these were the models that were ultimately used in producing the WRF chart data models, you see that the biases reaches several decimeters, at least onshore, and the standard deviation for the regional model, that is the NISE T model, is about 45 centimeter, while it is about 1 meter for the empirical ocean tide model that was produced by CSR. Offshore, it's the other way around. So the accuracy of the altimeter-derived tide model is better compared to the regional tide model. Still, it is in the order of a couple of decimeters. So the conclusion that we can draw from these studies is that anyway, the accuracy of the VOR product is largely driven by tide gauge estimates that were abundantly available in the UK region. In other regions, this is likely not the case. Okay, let's agree this was 15 years ago, and today's models are better, but there are some other conceptual problems that we outlined in the context of my PhD research. So back in 2010, this was not our main concern. And we agree, we knew that altimeter-derived tide models had poor performance in shallow waters. At the same time, we did have access to tide search models that did a reasonable job. But there are some conceptual problems and practical problems that I would like to introduce. First of all, remember the area of interest for which we need to obtain a Geodetic model. This is a zoom in. It's not the entire area, but it's a zoom in on the coastal areas of the Netherlands, and shows that we need an LAT model, a Geodetic model, inside the Wadden Sea and the eastern and western Scheldt estuaries. This is where we have our radar and tide gauge data. As you can see, there are hardly any satellite radar altimeter data available inside the coastal waters, and the number of tide gauges, these are the red squares as shown on the screen, that are equipped with GNSS are fairly low. At that time, there were only 3 tide gauges. Nowadays, it's a bit more, but still the majority of GNSS tide gauges is not equipped with GNSS. As such, we may wonder what is the accuracy of the mean sea surface model that we can obtain in coastal waters. The second aspect and conceptual problem is that the mean sea level is not the reference surface of an ocean tide model, at least not of the tide search models that we would like to consider and that were also considered in the VOR project. This can already be seen from the equations, because the gravity acceleration in the equations only acts in the vertical, which shows that the reference surface is by definition an equipotential surface. It can also be seen in a practical sense that if we would run such a model over a long time period and we would average the obtained tidal water level time series, the average water level obtained this way isn't equal to 0. So the tides contribute to mean sea level, which is due to nonlinear interactions. Furthermore, the tide search interactions are ignored. And remember that the IHO definition of LAT makes a reference that it is the lowest tide level under average meteorological conditions. So you may say that the nonlinear interaction between the tide and the average meteorological conditions, including the surge, are ignored. And finally, what is the average meteorological conditions? It is well known that the mean sea level in summer differs from the mean sea level in winter. And already in the North Sea, this is a signal with an amplitude of about 7 centimeters. So here's our approach. Instead of using the mean sea level as the intermediate reference surface, we use as an alternative the geoid or quasi-geoid, which in our country, in our region of interest, is practically the same. Which means that we need to use the hydrodynamic model to get the separation between LAT and the equipotential surface that we adopted as the reference in the Netherlands. This can be realized by adding the average meteorological conditions as forcing fields to the hydrodynamic model and a proper adjustment of the open boundary conditions, namely the water levels that are prescribed as open boundary conditions in the model. So here's the quick guide. If you want to know more on this procedure, in particular how to reference such a model in a way that it produces water levels with respect to the reference to a geoid, I refer to our publication in 2013. Otherwise, the procedure is again the same. You run the model over a 19-year time span, determine the minimum tidal water level, and interpolate it to the desired output grid. In our analysis, we also had to compute a quasi-geoid model because the model that was available at the start didn't cover the entire domain of interest. It was computed by gravimetric and altimeter data. In processing of the altimeter data, we again relied on the hydrodynamic model in order to reduce the sea surface heights, the instantaneous sea surface heights, to what we refer as geometric quasi-geoid heights. I'm not going to discuss these results further. Another difference compared to the approach that is used by the people in the UK is that we do not combine the observation-derived chart datum values at the tide gauges and the model output in a post-processing step, so by a kind of weighted interpolation, but we assimilated the observation-derived tidal water level time series into the hydrodynamic model. And this way, the physics of the model and the associated model observation uncertainties determine the contribution of both to the final chart datum surface. The last step is obvious. After having the geoid and chart datum with respect to the geoid or quasi-geoid, you add the two together and you have your chart datum. And here's the result. We have the quasi-geoid on the left-hand side. We added to that LAT with respect to the quasi-geoid, and in the right you can see our lowest astronomical tide model or chart datum model. The question now is, how consistent are we with the values derived from the tide gauge records? In the map, I show the difference between the observation and model-derived LAT values. And this is, by the way, LAT with respect to the quasi-geoid. Overall, the agreement is reasonable, which is also confirmed by the scatter plot that is shown in the right-hand side. There are some locations that behave as outliers, and typically these are the locations where the model lacks resolution. And most of these locations are in the Wadden Sea, where it is known that we need much higher spatial resolution than we had available in the model that we used. In the German Bight, that is indicated in the area here, the differences are relatively large because we do not assimilate any tide gauge record there. And the reason for that is that the tidal wave propagates around the Scottish coast all the way to the south. It is reflected by, let's say, the very southern North Sea, so the entrance to the English Channel, and then it moves upwards along the Dutch coast, which means that in order to improve the tides, we are way more interested in tide gauges along the UK coast than in tide gauges along the German and the Danish coast. Here are the statistics. So overall, we see an agreement up to the 10 centimeter level in the North Sea and about 24 centimeter in terms of RMS in the Wadden Sea. If we focus on the Dutch waters only, the statistics improve to 7 centimeter and 15 centimeters for the North Sea and Wadden Sea, respectively. You may wonder about the value of LAT in the Wadden Sea, because the Wadden Sea, as you may know, is an intertidal area. So large part of the time, there is no water, which means that LAT would correspond to the no water level. As a resulting fact, the LAT solution isn't smooth, and actually it doesn't make any sense to map bathymetry with respect to the no water level in a map, because then we would only have zeros. So what is done is a very engineering approach, which is not scientifically justified, but what we did is we realized a so-called pseudo-LAT solution, which was obtained by adding 2 meters of water to the open boundary conditions and also to the tidal water levels that we assimilated in the model. Then we did the same exercise, and in the end of the day, we computed pseudo-LAT, of course, after restoring the 2 meters back. And since this approach is not valid outside Dutch waters, in the final model we excluded the estimate in the German and Danish Wadden Sea. You may wonder why you did not use altimeter-derived tides or chart datum estimates derived from an empirical ocean tide model. And this is a fair question indeed. Well, my first response is we do use altimeter-derived tides to generate the tidal water levels that are prescribed as open boundary conditions. The open sea boundaries, and notice the model that we used is far larger than the area that I just showed on the map, but the open sea boundaries are in deep waters, and there the empirical ocean tide models do have good accuracy. However, in shelf and coastal waters, this is not the case. Stammer and colleagues conducted, to my knowledge, the latest assessment of global ocean tide models. And they found that the accuracy of the 8 major tidal constituents is 5 to 6 times lower in shelf and coastal waters than in open waters, the open ocean. And remember that this only reflects the 8 major constituents. This is confirmed by an analysis on the Northwest European continental shelf that was recently conducted by Greg and colleagues. They assessed the accuracy in multiple ways, but what way you choose, the order of magnitude of the accuracies found in their study is comparable to what has been found by Stammer and co-authors in 2014. It's multiple centimeter, 5-6 centimeter level. Why this is the case? This is a valid question, and one we also recently investigated. Before I get to our answer, it's helpful to remember that tides in shallow water are significantly more complex due to the presence of compound tides and overtides. These are generated through the nonlinear interactions, either between 2 or more major tidal constituents, which produce the compound tides, or through a single constituent that interacts with itself, which results in overtides. The result is the formation of new tidal constituents with frequencies that are either the sum or difference of the original constituent frequencies, or integer multiples of the original frequency. Secondly, we need to be aware that satellite altimeters have limited temporal sampling. And as a consequence, the energy from most tidal frequencies is aliased into lower frequencies that are within the sampled bandwidth, resulting in the well-known aliasing effect. And here's an example for an offshore tide gauge in the North Sea. So as you can see, the spectral analysis presented in the top figure shows that there is energy at way higher frequencies than what are sampled and determined by the Nyquist frequency of the altimeter record. All this energy maps into this bandwidth, giving rise to an, as I said, well-known aliasing effect. This is why we can only estimate a limited subset of all tidal constituents. And remember, the list of tidal constituents produced by the IHO contains more than 400 tidal constituents. In our study that we recently completed, we assessed the impact of the ignorance of nonlinear tide search interactions. These interactions, so these nonlinear tide interactions, alter the phase of tidal signals, while vice versa, the tides modulate the non-tidal signals. So in the context of tide search interaction, the tides are affected, the phase of the tide is affected by the presence of a surge, while vice versa, the tides modulate the surge. This effect is well known and reported in numerous locations globally. However, because of this, the total water level cannot be decomposed as the sum of tides and surge. And surge, again, are the variations due to wind and sea level pressure, baroclinic processes, and whatever. But this assumption, this is a key assumption in the altimeter processing. So before doing the tidal analysis, they remove as much as signal as possible. So they remove the tide correction and they remove surge corrections separately. What does that mean? Well, here you see on two maps that I show in a minute, the standard deviation of the residual water level time series at the TOPEX JSON altimeter points, obtained by applying two sets of correction. On the left-hand side, you will see the corrections that are typically applied in the altimeter data processing, where the nonlinear tide search interactions are ignored. On the right-hand side, you see corrections that we obtained with a hydrodynamic model, tide search model, where we include the nonlinear tide search interactions. And here's the difference. So as you can see, the standard deviations are way more larger over the entire shelf region, and notably in the coastal area, compared to what we obtain. And I dare to say, we didn't investigate it in detail, only at one particular location. I dare to say that this is not so much related to the quality of the DCSM model as such. So if we would compare DCSM tides to fast tides and DCSM surge to duck surge, the variance reduction I would expect is in the order, does have the same order of magnitude. It's really about the ignorance of the nonlinear tide search interaction. This is key to improve the tidal representation in hydrodynamic models. Here I again show the same map as before. What we now did was we used this residual water level time series to estimate residual tide corrections, and again apply these corrections in order to see whether we get an even further reduction of the standard deviations. And here's the result. So as you can see, is that in most of the coastal areas, we see a dramatic reduction of the standard deviations. So if we would compute, let's say, the total statistics, and we compare the estimate that we obtain in deep values compared to, in deep waters, compared to our median standard deviation that we obtain for the shallow waters, we are at about the same level of accuracy, which is good news. So by including tide search interaction in the altimeter processing prior to estimating tides, we can exploit altimeter data to improve the tidal representation of hydrodynamic models, and hence may expect an improvement of Geodesy models. And if our HydroLab research proposal will be granted, which is a cooperation work that we did together with many institutes surrounding us and also a lot of companies. This is what we will use in order to produce an ultimately derived, a long-track tidal product for the global oceans, at least inside the area covered by topox-adjacent satellites. Next, we will use this product to calibrate the global tide and surge model that is developed and maintained by Datum. And third, we will use this model to produce a global map of the separation between LAT and the ellipsoid, where I want to say that we will also assimilate tide gauge-derived water levels. I'm now at the end of my presentation. If you ask me what is the recommended approach, I will not give you an answer. I think this is something that you may need, let's say, to develop and figure out to some extent yourself. I want to provide and conclude by some suggestions. I would start with a simple approach, such as the one that I outlined in the very beginning. I also would advise you to be pragmatic. If you have an area where the waters are anyway deep and you have no issue with safety of navigation, then you may live with a lower accuracy anyway. To me, the main challenge lies in maintaining consistency among chart datum values derived from different sources. And the last recommendation I have is, rather than reinventing the wheel, I would advise you to align with established methodologies, in particular in countries that are surrounding you. And if you want to discuss anything, feel free to contact me. Thank you.
Thank you so much, Cornelius. I think everyone would agree that that's an amazing summary of putting such a complex problem in terms that we can understand it. And yeah, I think you went to the perfect level of detail. So thanks for the preparation of that wonderful presentation. Again, we have it recorded, so I'm sure people will be going back and reviewing that and reading some of the references you've made. That was fantastic. We've got a few minutes for some questions, so I'll open the floor. Do we have any questions from anybody, please? I'm gonna start off on one because I'm very curious to know more about the future work that you were talking about, because I think that addresses one of the critical issues going forward. You're looking to develop this global model of ellipsoid to chart datum surface. That almost answers a lot of the discussions and questions that we had before from people around, how do I do this in my country? This is going to be a wonderful step that you're going to be providing. So maybe you could let the people in here know, is this anything they could be doing that would support you, like any information that you would like from their countries that might help with this research you're going to be doing?
Yeah, this is a good question. Well, I think the decision whether or not the project gets granted is made in September, half September, I guess. So that will be we're really wondering what the committee will decide. But for sure, if that proposal is granted, we would love to have, let's say, any relevant tide gauge data, if that is not already publicly available, because this is key for having a good accuracy in the coastal waters, and in particular the area of interest. Your own country. The second aspect is, and this is of the key interest of particular the dredging companies that support this work, is they want to have this accepted as a standard. And this is a key challenge that we will address in the proposal. So computing such a model is one thing, but getting it accepted is a second thing. And I think this is also something that at some point in time may involve you guys as a potential users. It's our purpose to make the model publicly available. So that's for sure. So yes, you can help by improving it or providing us with necessary tide gauge data. Second, we would be helped by any validation efforts that you can conduct in your own region of interest. And third one, if we all agree, and of course we can incorporate your feedback, very valuable. But if at some point, the question comes, it would also help to consider it as and help in getting to a standard. And this is, I think, in anyone's interest if we can kind of come to an agreement at some point. So these are 3 points I would like to mention, but very, very valuable. And I get back to you. I hope I have some positive news in September. Otherwise, we have a different discussion, I would say.
Okay, thank you. I think that they're great suggestions, and we can definitely help with the standards component. I think us within the centre, we have good links with ISO and also the IHO. We do a range of events where we're doing things together. And I think this paper as well that Avid's already talked to you about and that we're going to keep working on, I think if we can build in some more information about this approach that you're talking about, it would be further demonstration of the value that brings to member states. I think that would support what you're doing a lot. Also, if you need sort of things like letters of support, that's the type of thing that we could provide you with. So please feel free to write to me if you'd like something like that, because I can definitely see a link here of what you're providing would be of great benefit to the member states.
Thanks.
Yes, we have a question here from a colleague in Indonesia, Cornelis.
Yeah. Thank you. My name is Febri. So I want to ask, in Indonesia, we have archipelagic area that may be similar to UK. That how long the distance, based on your expertise, distance between the tidal gate station and what is the consideration? Because in Indonesia, we have a different characteristic of the ocean. There is open water, there is a strait, there is many other characteristic of the sea. So what is the reason and how long the distance between the tidal gate? Thank you.
Just to make sure that I got the question. So the question is how long the record should be to be used, or how what is the distance between, let's say, the tide gauge and the computation point to use it? Is that the question, or was it the first one?
In order to validate the Datum model, is how long the distance between tidal gate station, regarding the concerning the specific the area of the characteristic of the ocean.
So you mean so if I have a coastal tide gauge and I have a model, let's say, what is kind of the representativeness of this chart datum estimate at the coastal tide gauge for the surrounding area? Is that the question?
Yeah.
I would say that really depends on the local situation. But as I just explained with the example of the tide gauge we have in it was Hoek van Holland, so at the new waterway, where the tide gauge is at the mouth of a river, then I would say it cannot be used only up to maybe a few hundreds meters offshore. And the point is that the influence of this freshwater lenses of freshwater is limited to the coastal band. So outside this area, and it can be maybe a few hundred meters up to a few kilometers, but outside this area, the tidal amplitude is different. If you have similar processes or a very complex morphology, coastal morphology, or a very complex bathymetry, I would again say that the representativeness of the chart datum estimate at the tide gauge is really limited. So typically what people do when doing such an analysis, and you have multiple tide gauges, you always include a kind of scatter plot showing the distance from the tide gauge to the validation site, let's say, and the accuracy level. And what you then see is that as the distance increases, of course, the separation also increases. But I would say in complex situations, you should think in the order of hundreds of meters to a few kilometers.
Okay, thank you.
Thanks, Cornelis. And just one last question I had. We were talking a lot about uncertainty this morning, and I know that's been an issue with some of the other global models as well. I was curious, are you looking to have some sort of location-specific uncertainty included in the proposed model you're going to be developing?
That's a good question. What we wrote so far is that in the proposal, what we foresee is that validation is conducted by validation comparison. We will compare our model to any regional models that are publicly available, and in particular, the dredging companies that are involved in the proposal do have access to certain models. So we can do something there. And we would like to consider a subset of tide gauges where that we will not use in the data assimilation. Otherwise, it becomes very, very challenging, I would say.
Yeah. Okay. Thank you very much. That's good to understand what the plans are. Please all join me again in thanking Cornelis for a wonderful presentation.
Thanks. It was a real pleasure. And feel free to contact me in case of any doubts or questions or whatsoever.
We will, certainly. Thank you very much for all your help, and look forward to hearing from you soon. All right. Bye for now.
Yeah.
Thank you.
Bye.